to the fundamental theorem of calculus. So this video will cover fundamental theorem of calculus part 1, and then we'll do fundamental theorem of calculus part 2, and then we'll go into how this affects area between two curves. So the fundamental theorem of calculus, it goes through this one. If f is continuous on the closed interval a to b, then the function f of x equals the integral of a to x f of t dt has a derivative at every point of x in the interval, and the derivative of the antiderivative, I guess, would be the d dx. Notice the writing it, the derivative of the integral of f of t dt is just f of x. So this is kind of like, you know, if you have the square root of 4 squared, it's just 4 because these two cancel each other out. And this is the same idea, but we're replacing x because they're asking you for the derivative with respect to x. So these two guys are going to cancel each other out, and you're left with f of t dt. Oh, this cancels out as well. But they want it in terms of x, not t, so it becomes f of x. That's main idea. Don't overthink that one. Okay, so we continue on with this one, the derivative of the integral. Every continuous function f is the derivative of some other function. Now, they are referring to this guy here at this point. This is where we get to go back to chapter 3 when we talked about continuity, that continuous did not mean differentiable, but differentiable did mean continuous. And this guy is a derivative of some other function. Every continuous function has an antiderivative, and then the process of integration and differentiation are inverses of one another. So basically, one will undo what the other one did. Okay, so we're going to apply the fundamental theorem of calculus, and a couple of these I'm going to prove the answer instead of just writing the answer down. This one is going to be 1. I'm going to write down the answer first, and then we're going to go through and we're going to prove that that is the answer. So according to the fundamental theorem of calculus, the derivative and antiderivative, the derivative and integral will cancel each other out, but we want our answer in terms of x and not in t. So my answer would be sine of x. Done. That's all there is to it. According to the fundamental theorem of calculus, the answer is sine of x. Now, I'm going to prove that this is the answer by actually going through the steps. So I'm going to do the antiderivative, and then I'll do the derivative, because just like anything else, you work from the inside out. So if I take the integral of pi to x of sine of t dt, t, well, the antiderivative of sine is cosine, but the derivative of cosine is usually negative sign. No negative here, so we put it here. And I need to evaluate this from pi to x. So that gives me negative cosine of x minus pi. You guys have already seen how to use this one. And so we go through, not pi, it's cosine of pi. I'm awake, I really am. Just working ahead of myself, sorry. Cosine of pi. So if I distribute the negative sign through, I get cosine of x negative plus cosine of pi. For those who know their trig, they know cosine of pi is -1. So this is really negative cosine of x minus 1. There's the antiderivative. So anyways, I did the integration. Now I want the derivative with respect to x of negative cosine of x minus 1. Well, derivative of cosine is negative sine, but this negative out front, so I'm going to write this anyways. Negative sine of x minus the derivative of any constant is 0. And then we got 2 negatives make it positive, so my answer is just simply sine of x, which is what we came up with earlier. Now, on like an AP exam or whatever, you're not going to just write, oh, the answer is sine of x. Of according to the fundamental theorem of calculus, you can write it. So anytime you use a theorem, you need to identify it. I'm using this theorem, that way you don't have to prove the answer. According to the fundamental theorem of calculus, the answer here is sine of x. Otherwise, yeah, you're going through all of this process. Okay, so let's look at the next one. So this one here has 0 to x of t cubed minus t, all of that to the 5th power, dt. Lost the dt somewhere. And they're asking you for the derivative. So really, they're going, I want d dx of the integral of 0 to x of t cubed minus t quantity to the 5th power dt. And according to the fundamental theorem of calculus, the answer is x cubed minus x, all that raised to the 5th power. There's your answer. Now, you can go the long way through this one if you wanted to. I would not. But that's all we needed. Okay, so again, yes, I forgot my dt. So again, they're asking you for the derivative with respect to x of the integral of 0 to x, 1 over 1 plus t squared dt. And then you guys go, well, according to the fundamental theorem of calculus, this would be 1 over 1 plus x squared. And then, of course, in class, I ask students, I go, what is this? You should recognize this as being a derivative of arctangent. Okay, so what if they have something more than x up there? So I'm going to give you an answer again, and then I'm going to go through and I'm going to prove what the answer is. So this one here, yeah, I would take x squared and put it in terms of t. So this is sine of x squared times 2x. Now, if you want, wait, where that 2x came from? Remember when I did the antiderivative, x squared fell into the problem. But when I did the derivative of that, now I have to do the derivative of x squared. Now, if you go, why didn't we do this on the earlier problems? It's because it was just x, and the derivative of x is 1. So we really did, we just didn't see it. So here we go. We're going to prove this answer again, so you guys aren't questioning me too much. So proof, and this is not a proof that this works every time. This is a proof of this answer. So first we integrate. Integrate 1 to x squared of sine of t dt. And we've already done this one in an earlier example. Derivative of that is, or antiderivative of that is negative cosine of t, evaluated from 1 to x squared. So this gives me negative cosine of x squared minus cosine of 1, or negative cosine of x squared plus cosine of 1. Now, this is not on the unit circle, so we're just going to identify the fact that it is some constant. But this is our antiderivative. We could stop there. That's the antiderivative. But we want the derivative of the antiderivative. So I'm not going to skip any steps. I'm going to do a little chain rules side work over here for you. Now, some people can go through it very quickly, going derivative of the inside times the derivative of the outside, evaluate. Let's just go through it. Inside. The inside is going to be x squared. So the derivative of the inside is 2x. Outside is negative cosine of the inside. And the outside prime is going to be sine of I, because negative sign, but two negatives make it positive. And then the derivative is I prime times the inside prime times the outside prime, or 2x sine of the inside. So the derivative of negative cosine of x squared is 2x sine of x squared plus, and the derivative of constant is 0. So there it is, our derivative is here, which is exactly what I had given you earlier. So this is one of those that don't, and I want to point out this negative sign, that if we could have ignored the negative, because one would have given me the negative and the other one would have taken it away. And that's going to happen on a couple of these other problems here in a minute. This one. So keep in mind the chain rule that this guy here, so you can claim it to be u equals x squared, u prime is 2x. Or if you want to change that to t, since that's where you're substituting things into. So this gives us 2x e to the x squared power. And there you guys have it. So this is what we have on this one here. All right, let's try another one. What about this one? So we can claim t to be x squared, so t prime is 2x, which gives us an answer here of 2x cotangent of 3x squared. Now, if you're trying to figure out what happened to this 3 here, when we had the antiderivative, when we do a derivative, we would multiply by that 3. But when we do the antiderivative of that, we would have divided that by 3. So anyways, the 3's would have canceled each other out. That's why we don't have to worry about it anymore. Okay, so let's look at a little bit more. Variable lower limits of integration. They want you still to find this one here. But we have to use one of those rules in the front. And so we're going to go with y equals negative, and then we can change our limits of integration. 5 to x of t sine of t dt. And now we can go through and put our x's where they belong. So we get negative x sine of x. There is our derivative of our integral. It is still asking us for the derivative. So on this one here, we just throw the negative on the outside, and there's our answer. Okay, now notice that we got more going on here, and we can't do this one the way we've done before, so we have to separate them. So we're going to just rewrite it as 0 to x squared of 1 over 2 plus e to the t dt plus 0 to 2x. Okay, let me go with, oops, not plus, this is going to be subtraction. Sorry. Because what we're looking at is we're having from x squared to 2x, and what we have to do, if we're going to go from 0 to x squared, that means we're starting at y equals 0 to whatever x squared is. Remember, those are going to be your values, your y values. And so we're starting from the bottom up, and so at that point, what we got to do is subtract the difference of one over the other. Anyway, and because what we've done is separate them. So we just look at the two. Now we can do this with the derivative and everything else. So in this one, t is going to be x squared, so t prime will be 2x. So this one, keep in mind, they're still asking for derivatives. This is going to be 2x over 2 plus e to the x squared minus, and on this one, t is equal to 2x, so t prime equals 2. So we get 2 over 2 plus e to the 2x. And there's your answer on that one. And basically what we did is that if you have we know x squared does this bit, okay, it actually comes down. Okay, force that one there. And then 2x goes this way, and the x squared is going to come up. Really, we're looking for this information here. Now, before you tell me, hey, you subtracted these, the picture would make more sense if I had them actually labeled out, because they would cross at x equals 2. And that's when the one would go below and the other one would go above. So some people look at this going, wait a second, this guy's on top. We've got to do it in the order they gave it to us in. So I don't want you thinking, well, hey, wait a second. We have to do this in the order in which they gave it to us in. So we just looked at 0 to x squared minus the other, and it's what it's going to do. Yeah, we'll get a negative value if we actually calculated values. But we're going to, but keep in mind, we're not, these are these values. And we don't know necessarily what that's going to do to the function itself. So, but what we're saying is it's the equivalent of grabbing what's inside. That's why we subtract. Okay, so let's look at another one. We got to break these two apart as well. Still asking us for a derivative. This is going to be 0 to x cubed of cosine of 2t dt minus 0 to x squared cosine of 2t dt. And we can go through, if t is x cubed, then derivative would be 3x squared. So this one would give us 3x squared cosine of 2x cubed minus, and then this one, the t would be x squared, so t prime would be 2x. So this would be 2x cosine of 2x squared. And there's your answer. That's the derivative of the antiderivative, evaluated at x cubed and x squared. All right. We're almost done here. I know we're getting close to 20 minutes. We're going to do the same thing on this one here. So we'll separate it out. So 0 to cosine of x of t squared dt minus 0 to sine of x t squared dt. I want to point something out to you on the other problem. I was going, oh, it looks like the area. No, this is actually the second part of the fundamental theorem of calculus that we're using. And the idea of that we do the antiderivative, we do the upper bound minus the lower bound, and that's why we're doing it this way here. But we're separating that out instead of doing one particular problem. So this one here, let's pay attention, the cosine of x. So if t is equal to cosine, then t prime is equal to negative sine. So we get negative sine of x cosine squared of x, because the cosine of x is going in place, minus, and then we can do the same thing over here. If t is equal to sine of x, then t prime is cosine of x. So this one's going to give me cosine of x times sine squared of x. Now you can play with this to try and make it look prettier if you want, but we're not going to go there. Okay, so keep in mind if you have the variable on the top and bottom on the upper and lower limits, you just have to separate them out. Okay, just a few more things to go and then we'll be done with these. Constructing a function with a given derivative and value. So it says find a function y equals f of x with derivative of this that satisfies the condition of f of 3 equals 5. So they want you to write an integral. So you go, all right, cool, the integral of tangent of t dt. Yes, we're taking the x out, and we're going to put the x on top, just like we've done before. So we're kind of going backwards on the last problems. But down here, what we need to put in there is 3. Because this is a reminder that if the limits of integration are exactly the same, you're going to get an answer of 0. Sorry, you're going to get an answer of 0. So I put x up here, 3 down here. So when I get 3, the whole thing goes to 0. But I want f of 3 to be 5. So in the end, I just do plus 5. So remember, the find a function f of x with the derivative of this that satisfies the condition that f of 3 equals 5. And if you keep in mind that you do derivative of an integral, you get back to this guy here. And I would put x in. So there you guys have it. But this part here, this part is not under the integral, so you wouldn't do that. That would just be plus 5 in the end. But this one would give me 0. Okay, so let's try this one again. So I want cosine squared of 5x, cosine squared of 5x. I want y to be -2 when x is 7. So we write out the integral. X is on top, and the 7's on bottom. And we're just going to write all of this, but we're going to change the x to t. So this is going to be cosine squared of 5t dt. And when the limits of integration are exactly the same, I want my answer to be -2. So -2. Because at 7, this whole thing here will go to 0. Okay, one more. So integral 0 to x, that's 0, of e to the square root of t dt, and I want that to be 1 when x is 0. Don't overthink this, it's just a matter of rewriting it to get the answer you want. Okay, that is where we're going to do a pause and stop. And the next video will be on the second part of fundamental theorem of calculus. Good luck.